you. All right, so as most of you have guessed, there are more than 1,500 languages, programming languages out there, and all of them have been invented since the 1950s, more or less. And this is a bit surprising, because when you think about it, all these languages, from a mathematical point of view, are exactly equivalent. They can only do as much as the other. So I think the reason why there is a proliferation of languages is, one, they're cool, and two, there's been a lot of effort, both in the industry and in academia, to try and design languages that are easy to use. Because the time that it takes to create a program is, it costs money. Another thing that's emerged from the industry is the idea that we should try not only to look at speed, at how fast the computer goes, but try first to make sure that the code we do is correct. Okay? If you guys have ever had to reboot Windows, you know what I'm talking about. We want code that works. To try and tell you why this is important for why this is important for science as well, let me try and tell you a story, okay? Imagine that we have a God walking this earth. And this God is not necessarily a good God. It's a mischievous God, okay? This God decides from time to time to tweak the laws of physics. So what would physicists have to do? Well, they would have to figure out what laws have been tweaked. They would have to rerun all the experiments ever done in history to try and figure out what is reality again. They would have to rerun LIGO, but they would also have to have a PhD student throwing apples at their advisor just to figure out gravity again. So programmers, we're kind of gods as well, because we get to code stuff into a program and decide what the laws of physics within that program, what the laws of nature within the programs are. Now, the problem is we're also human. So sometimes when we add stuff to a program, we do it wrong. We don't talk to the computer the right way, and it does something other than what we expect. Or what we introduced in a program has a knock-on effects, and a change here can affect the program elsewhere. So being both able to determine what the laws of nature are, changing them constantly when we're adding features, that means that we have, again, to rerun every experiment that we've ever done to prove that the code is correct every time. Now, this is why trying to write the code, try to focus on software correctness rather than on speed is of great importance to programming. So what does that mean? Well, that means that we should write code to be readable. Code first should be easy to tell from looking at a code, what it is that it is intended to do. It should be reliable. It should work in all different sorts, in all the different situations that it can be confronted with. And then finally, we should wonder about performance. Performance is basically the last item on our priorities when we write software. If we go into more details, we'd add stuff like deployability, the ability to take a code from one RA's desktop where it was first created to another RA's desktop, to Grace, to Legion, to supercomputers left and right, from Linux to Windows to Mac OS and whatnot. And then we have sustainability, the ability to add new features without having to employ 10 PhDs to figure out what exactly the code does. So the cost of adding new features. And again, performance is only at the bottom of the list. It's really a consequence of all the rest that comes before it. So why should we not care about correctness? Well, or not make it a focus of the programming? Well, because one answer is because the program is always correct. Okay, that actually never happens. Another is because the output looks kind of right and will go through peer review without problems. Sure, why not? Or because the RA or a student or a PhD student likes to spend time debugging rather than doing science. If these are not true for you, then correctness should be a focus of the programming done in your lab. So how do we do it? Well, The analog of experiments in programming is testing. The scientific method applied to programming is writing tests. These are basically, you can think of it as sorry, I lost my thread there. So what are tests? Well, they ensure that programs do what they should. That's the main gist of it. They are also, so they're little experiments that take a block of code and run it through its pace. Given a set input, we figure out what the set output or the kind of behaviors that it does. Okay? So it basically is a small experiment for each block of code. But it's also a runnable specification. The next RA student will come in, look at these tests and say, okay, this is the input that this function is supposed to take, and this is the output that it takes, that comes out of it. Now I can understand what the code does. They are runnable. If you compile the code and run these tests, you know immediately whether the code is up to date, as opposed to documentation, which goes out of scope as the program evolves. It helps write code that is modular, because we have to slot these small blocks of code to run experiments on them. It makes sure that we can slot them left and right, and that means that we can reuse them left and right. That makes the cost of adding new science to a code a lot less. So there's different kind of tests. There's the regression tests. Regression tests are basically, we have an oracle that tells us what the output of a code is, and generally that oracle the program itself. So the regression tests are telling us that a code is just as correct today as it was yesterday. Or another way to put it, it's just as wrong today as it was yesterday. It ensures that when we add features, we haven't done anything to a code. We have functional testing. That's the step up, where we have a pen and paper answer to a pen and paper program, pen and paper problem that we can test against. The most important are the unit tests. This is really where we can take each block of code, slot it out, run experiments against it, and check that it behaves as it should. This is our magic a baton or something to code less and do more science. This is our magic trick as far as professional programmers are concerned. This is how we save time. So the next step up is then to run these tests automatically each time changes are made to the code. And this is a service we offer at UCL's, at RITS. So if you have code and you want it tested all the time, each time you push changes to version control, we can help you out. So get in touch with us. All right, so let me give you an example of how correctness helps build better code. This is one of the first projects we were involved with. It's a software to analyze single ion channel recordings, and it was software. The software was developed in the Faculty of Life Sciences by David Colquhoun over the past 40 years, and it's now owned, I think, by Lucia Silvilotti and Remy Lappé. So what single ion channel recording is basically we're dropping a pipette, or they're dropping a pipette over a cell, and which englobes this one single ion channel. This is basically a door that opens and closes and lets stuff in selectively into the cell. And in the micropipette, you can have drugs and stuff to check what happens when you have when you put these drugs into around the cell. The kind of recording we have are here. Basically, we are checking the electric potential between the inside and the outside of the cell, and we get different signals when the channel is open or closed. From this kind of data, open and close times, the program figures out the number of steps that it takes to open a channel and how fast these steps are. So when we first started the project, This software only ran on Windows XP. It had not been compiled since 2006, and it couldn't run on anywhere except on these few machines that they were keeping in the lab for that very purpose, more or less. So what we did was to transform this code from a mess into something that is much more readable in C++ and Python. Again, our focus here was to create usable code. We focused, of course, on reliability, and we made sure that we had a set of unit tests that checked every bits of code. So we went from having people running tests by hand to check whether they installed their code or not, to having having a computer test it for us. And of course, the code works on more machines than those particular Windows XP. At no point did we really look, in the first 6 months when we rewrote the software, at no point did we look at performance. We just didn't have that time. But eventually, despite that, the code was just as fast as the original Fortran code. So performance just came out of everything else. This project was then picked up fairly recently with an ECSC grant. And at this point, we wanted, among other things, to look at performance. So we did a bit of profiling, Jens Nielsen in our group found that there was a lot of memory allocations going on, and he figured out a way to remove those memory allocations by changing the type of the matrices underlying all the math. So this is a very deep change. What it means is that if you make this change, you could really affect everything, every computation across the whole software. But because we have tests, we could make those changes and check immediately whether the calculations were affected. Eventually, I think it took a few weeks, or probably 2 weeks or something, what we find is that now the code is 50% faster. So it's twice as fast as the original Fortran code. This is basically 6 months of rewriting a code correctly, and then 2 months of trying to look for 2 weeks of looking for performance. That's what relying on correctness rather than on trying to just get a few benchmarks out. That's what it gives us. Thank you.